friends, welcome to the channel Physics by IITians. Today we will discuss the new topic of laser, and yesterday I told you what are the topics to be covered. So let's start. Today our very fundamental topic is the laser, and the fundamental question is why laser? Because it has some unique properties. Unique properties like it has high monochromaticity, it has narrow spectral width, it is highly coherent. Now, do you know the meaning of all the things? Look, highly monochromatic means if you have a lambda, that is a particular wavelength lambda, and if the laser light is consisting only with a single lambda, then that light should be called monochromatic. Or any light which is consisting only with a single lambda, because white light is not a monochromatic light, it is a combination of different wavelengths. So the light which having a single wavelength or almost a single wavelength, you can tell it a monochromatic light. So for the laser case, it has a single wavelength, so it is highly monochromatic. Now the narrow spectral width. What do you mean by spectral width? Suppose you draw a spectrum of a light, then you record the intensity and you draw intensity versus wavelength, you plot it and you get some kind of graph like this distribution. So this width, that is the delta lambda, and the peak wavelength is lambda. How do you get this? I mean, whenever in spectroscopy also we record spectrum of some molecules, atoms, so we usually record in terms of wave number or in terms of wavelength. Okay, we record the intensity and we get a distribution like this. So for if suppose this is a narrow spectral width, so the width of this spectrum should be much narrower, means lambda naught is much, delta lambda is much lower. But for a broad spectrum, what does it mean? For a broad spectrum, it is like this. I mean, the delta lambda in that case will be much greater. Okay. Now, I am asking a question that if you have a single frequency line, okay, suppose there are two levels and there is a transition from upper level to a lower level. So you will get a single wavelength, that is lambda, and you want to find out the spectrum in terms of its frequency and intensity. How do you plot it? Okay, let's plot it. That you have just two levels, and if there is an optical transition from the upper state to lower state, so you will get a certain frequency of light or emitted light or certain wavelength of emitted light. So you plot the intensity versus nu, and the nu you will tell me that theoretically it should consist of one nu, that is you should get a delta function like line, but practically you don't get it. Always have some certain width. What is the reason behind that certain width delta nu? Because from the energy uncertainty, that is Heisenberg energy uncertainty principle, we always know that delta E into delta T is greater than equals to some Planck constant by 2, h cross by 2. So however, if there is a certain, I mean specific, you are specifying the two energy levels, but the energy levels itself has some energy width, that is E1 plus delta E1 or E0 plus delta E0. So there is inbuilt uncertainty in the frequencies of the light. So you cannot get exactly a single line whether the transitions are going to happen with the two levels. So it always have some spectral width or natural width, and in case of laser, the natural width should be minimum, and that's why it is called the narrow spectral width. Okay. Now it is highly coherent. What do you mean by coherence? Coherence means, suppose you have a light, and you can think of light as a radiation, that is a combination of electric field, magnetic field, electromagnetic wave. So electromagnetic wave, so suppose the electric fields are oscillating sine wave. This is a pure sine wave. So whether this sine wave is extending from minus infinity to plus infinity, so you can tell that this light is purely coherent, highly coherent light. If you take another light which is also purely sinusoidal light, so at any point, whether you are here or you are here, you can tell that these two waves are purely coherent. In other videos I will broadly discuss about the coherence. Now for this time you understand it as this is a pure sine wave, but I am telling the theoretical thing that minus infinite to plus infinite extension, but in reality there is nothing pure up to minus infinite to infinite distances. So in case of laser, the coherency will be up to a certain distance or up to a certain time. If it is coherent up to a certain distance, that will be spatially coherent. If it is coherent up to a certain time, it is called temporally coherent. So the correlation between the waves, they have some definite phase relation. Whether the phase difference may be 0 or may be constant. Okay. Now, how can you get this? What are the ideas behind the laser? So laser was invented in 1960s, nearly about, okay, and the inventor was H. Townes. In his word that at that time there was no laser, but there was oscillator, and the oscillator is electric oscillator. So what does it do? Oscillator, you in some oscillating arrived radio waves antenna, you have an oscillator, it will amplify the signal, and you can get the signal. Okay, so if we do the same thing, that we have a certain signal, and somehow we can oscillate it to amplify the signal so that we can get a better signal. That is in terms of the light, that you have certain light and you will somehow amplify the light and you will get a better light, that is you get another intense light, that is laser. That's why the basic I take the title of today's lecture is production of coherent radiation by atoms and molecules. So we can understand what do you mean by coherent radiation. Now we will understand how to produce the coherent radiation by atoms or molecules. So Townes himself thought that if we can think that atoms or molecules are itself as an oscillator, because whenever atoms or molecules there are bound electrons or with the ions, so whenever it is an incident with an electromagnetic field, so there will be oscillating dipoles. So whenever there is oscillating dipoles, so atoms can radiate, because the accelerating charge dipoles can radiate electromagnetic radiation. Now you have to think that you have a laser medium, that is it is producing electromagnetic wave. So it is a cavity. So cavity is producing radiation. So you will directly goes to the Max Planck hypothesis for the black body radiation. Okay. So in case of black body radiation, Max Planck formulated that the energy density or the rate of transition, that is the rate probability of transition P, is directly proportional to the energy density of the incident electric field. Now this energy density of the incident electric field is directly proportional to omega, that is frequency of the electric field. And now since an unpolarized light can have many polarizing direction, so the omega is not unidirectional, because the incident light is not polarized light. So omega is not unidirectional. So there shouldn't be any correlation between the lights which are producing by the oscillating dipoles, because you have to think that suppose you have a dipole, you have another dipole. Dipoles means oscillating inside the atom, inside the cavity, and they are exposed to different electric fields due to electric fields of different directions. So the fields, the electric field which they will radiate, they don't have any correlation of the phases between the phases. So accordingly, according to Maxwell black body radiation law, we cannot produce any coherent light from the this kind of black body radiation theory. So because also we have to think that from Maxwell's whenever we are doing Planck's radiation law, we are applying thermodynamic equilibrium. So at thermodynamic equilibrium, we have Maxwell-Boltzmann's law, that is n suppose n1 equals to n naught e to the power minus delta E by kt, that is the population at the level, suppose this is the 1 and this is the 0th level. So population at the level 1 is related to population at the level 0 will be e to the power minus delta E by kt, that is n1 is always less than n0 at any temperature T. So this is the condition for the thermodynamic equilibrium. Now we have to know that in case if we want to get lasing action, what should be the population? I mean, is this thermodynamic equilibrium relation will satisfy the lasing action, or we have to think over it? So Maxwell did a lot of work over Planck's hypothesis or Planck's blackbody radiation, and he calculated that the rate of change of electromagnetic energy confined in a region where it interacts with a group of molecules must have the form. What is the form? This is the rate of change of intensity. It must be a form with the spontaneous emission, with the spontaneous absorption, and with the stimulated emission. So what does it mean? Let me erase it first. So the term by term meaning is, suppose you have two levels, one with the level of energy EB, another with the level of energy EA, and one with the population Na and another with the population Nb. Suppose there are atoms and you somehow it is incident with the electromagnetic field. Okay. Now it will get excited and absorb the radiation, it will get excited and it will go to the upper state. So this is called the spontaneous emission, and this spontaneous emission absorption, and this should depend on the intensity of the incident light. So this should be proportional to I, and also the population at this level. Okay, Na. So they should be a factor which should be proportional to I into Na. Suppose this is Na, and now I thought that it was Na prime, but this is Na. Okay. Now this is the spontaneous absorption. Now whenever the light gets to the excited state, it has some certain lifetime, because it cannot stay here abruptly for longer time, because at this stage the atoms is not a stable situation. So it needs to be come to the ground state to be stable. So to be stable, it automatically comes to a ground state, and it is independent of the incident intensity of the light or energy density of the light. So the next term, that is, this is, I tell you, the spontaneous absorption term, which is proportional to the incident radiation as well as the population at the ground level. Now there should be a spontaneous emission, which will be only proportional to the number of the atoms which is staying at excited level. So there should be not dependency of the incident intensity or energy density of the incident field. Now there will be another kind of process which is called stimulated emission, and it is like that you have already electron or atom which is excited state. Now somehow an incident electromagnetic wave or light of energy h nu will stimulate the atom to radiate, and it will come to the ground state. So it will also radiate, and also the incident light which was going to stimulate the atom to come back to its ground state, so it will also radiate. So from one radiation, one photon, you are getting two photons. Okay. So this is called the stimulated radiation, stimulated emission. This should be proportional to the incident radiation, incident electric field or incident energy density, and also it should be proportional to the numbers of the atoms which are staying at the excited state. So this should be proportional to the intensity or energy density of the electric field and Nb. So stimulated emission E proportional to I Nb. Now the rate of the di by dt will be A into Nb, that is for the spontaneous emission, minus the spontaneous absorption plus the spontaneous stimulated emission. Okay. So Now, you are taking the differences between the emission, rate of emission and rate of absorption. So you take the two emissions minus absorption. Okay, now let's see what happens. So at thermodynamic equilibrium, when dIdt is 0, that is rate of emission is equals to rate of transmission, or rate of absorption is equals to rate of emission. So dIdt should be 0. You will get that I should be A N B by B Na minus B prime and B. Okay. Now, at thermodynamic equilibrium, this is the Maxwell-Boltzmann law. So, if this is satisfied, then NB dIdt at thermodynamic equilibrium, you don't get any population inversion, because always the NB is less than Na. Now, somehow, if NB is greater than Na, what will happen? If somehow NB is greater than Na, then dIdt will be positive. Means dIdt should be greater than 0 and the radiation will be amplified. That is, you are putting the lower energy and you are getting a higher energy. So you are taking it as an oscillator. This is working as an oscillator. Okay. So let's go. You cannot understand if you don't understand from the atomic level. Let's be physical. Okay. Suppose you want to make an oscillator. What is the properties of the oscillator? Suppose you have a pendulum, okay, and you are somehow the pendulum is oscillating, okay, oscillating like this. So it has some certain frequency, and if the length of the pendulum is L, so the frequency, natural frequency will be 1 by 2 by root over G by L. So the frequency, you all know that if I plot, if there is no damping, if I plot the intensity, it should be oscillating like this way. I mean, it will be oscillating without any problem. There will be, if there is no damping, it will be oscillating for lifetime. But it is not the present case. In case there are dampings, so in reality, so there is a damped oscillation. Now also you look another, you have a mass and it is attached to a spring. So it is also oscillating with the frequency. Similarly, you have a string and it is plucked, and if it is oscillating, it has also some oscillating frequency. If you have LC circuit, it will also have some oscillating frequency. But everything in the oscillation, it will get damped due to some damping or losses inside the oscillator. Okay. So if somehow you get that the damping term is there is no damping term, means what you have to do, you take a person and you tell him, please push the ball, please push it, periodically. Okay, so a person who is pushing the pendulum continuously, so it will go, it will come back, it will again be pushed, go, come back, go, come back. So someone is giving the feedback which is positive, or someone is doing a work to get the oscillation continuous. Okay, so that there will be no loss. So if you do the same thing in case of the atom, so in case of atom, there should be something which will magnify the amplify the oscillation. So if we put two mirrors here, that is, you have an active medium where population inversion is giving. You have a laser medium which can build up a NB is greater than Na. So upper level population is greater than the lower level population, and they are stimulating emission of radiations. So it is continuously go back. It will reflect from the mirror and it will come back to the another mirror. It will then reflect. It will come back. Okay. So this is kind of the someone is oscillating inside the resonator. It is this kind of configuration is called the resonator. So what we have learned today, that for the laser we need active medium which is capable of population inversion. Means the inversion, you need a higher medium that is largely populated than a lower medium. Okay, and another is that population inversion may be in various ways. This process is called the pumping. So the pumping process, it may be the optical pumping, it may be the biasing. Some another means of you have some kind of biasing, forward bias, and it may be also the resonating energy transfer, just like helium neon laser. the helium will somehow give the neon or the energy to the neon atom, and it will then give lasing action. So this is we will go much more details, and last one is the resonator, which is giving us a positive feedback to our medium to resonate for the lasing action. Now in the another video, the next class, we will some of the other things that what we need that to achieve monochromaticity, to achieve coherence, what we will do to get the proper laser medium. So for today, it's enough for today. So please, if you like the video, do subscribe our channel and like the video. And if you have any doubt, please do comment. Thank you.